we're going to see how to find the integrating factor in a differential equation that is non-exact. So we have the form of n of x and y, that is a function of x and y, dx, plus a function of x and y, n, dy, equals 0. This is a homogeneous equation. A homogeneous in differential equation means two things. One, that the right side is equal to 0, and the other, and we will talk in about this in other videos, and also there are already some videos about the other kind of homogeneous equation in which you would do the substitution of y over x, but whatever. So here we have this function. This you can see that we have this is a differential equation, and so here we have the solution to the differential equation. That remember that this solution is a family of equations. So it would be y equals to whatever. When you see this, you could say that m is the partial derivative of this function with respect to x, and this is the partial derivative of y of this function with respect the partial derivative of this function with respect to y. So first, when we have a differential equation like this, what we do is, if it is exact, that means that the partial derivative, that is the second partial derivatives are going to be the same. The mixed second partial derivatives are going to be the same. Mixed partial derivatives would be if this was the partial derivative of this with respect to x, now the partial derivative of this with respect to y is the same as the partial derivative of this with respect to x. This means that the equation is exact, and so we can find the solution by just integrating, for example, this with respect to the x in order to return to the previous equation, and we would have whatever function f of x and y plus c as always, but this c could be just a constant or could be a function only of y, that when we take the partial derivative of that function, because it's the partial derivative of x, would be 0. So for that, when you integrate m, you need to put plus a function of y. Hello, that function could be just a constant. And then you take the partial derivative of this with respect to y, and so this would be, well, all this that is supposed to be the solution. When you take the partial derivative of y, you should have this. So you would have the f in partial dy plus the h in partial dy is equal to n. If this is not the same as this, that means that there is this function. That means that this is not 0. And so you solve for this. And then you integrate. In order to have h, you integrate with respect to y. And then you have the equation. We have a lot of videos about this. You can do this way, or all the videos have done in this way, but you could have do it like you integrate n with respect to y, and here you add a function of x. You took the partial derivative of this with respect to x, and you equate that to m, and then you see and you find for m if for this, if this need, and then you have the solution. But so now, if the equation is not exact, you can multiply everything times a integrating factor that will make the equation exact. That is, the second mixed partial derivatives would be the same. There is a way that is just into the integral of here depends on if you have the equation of a differential equation, a first order simple linear differential equation, that is, let's say y prime plus p of x y equals 0, for example, in order to do it homogeneous. The integrating factor would be the integral of this, that is, of the function p of x, and then dx, and then you multiply everything times this e to the integral of this. You put it here, and then it will be exact. Notice that this is the same as this, just put in other way. Here you have dy dx if you want to put it as here, you will send this to the other side, minus, and you multiply this times dx, and you have dy equals whatever dx, and then you put one of them here and equals to 0 again, but whatever, is exactly the same. And we have a lot of examples of everything here. I also made a video of how to do the integrating factor, but it was cut in many videos for technical issues and things along that line. So I'm going to do another video, that is this, of how to find the integrating factor only when you have m and n. That is, you don't need to put it in this way, the normal way of the first linear order differential equation. But so let's go to find that integrating factor. That is the goal of this video. And we're not going to find it only as the usual way, that would be with m, but also with n. You will know how to do it. Alright, so we know that when we multiply by integrating factor, the equation is going to be exact. So let's call mu of xy mu of xy, mu first, mu of xy. Mu of xy is going to be the integrating factor. So you multiply everything and you will have mu of xy times mxy dx plus mu xy n of xy dy is equal to 0. And we know that this is exact, so we know that the partial derivative of this, that is what is inside of, or what that is multiplied by dx, the partial derivative of this with respect to y is going to be the same as the partial derivative of this with respect to x. So we have this mu m in the mu xy mxy in dy is equal to partial derivative of mu xy nxy divided by dx in dx. Next, yes, we know that, well, not always, but we assume that there is an integrating factor that will make this equation, this differential equation, exact. So for that, we are trying to find the integrating factor. Also, we will assume that that integrating factor depends only on, let's say, x. So now it is not mu of xy, so now it's mu of x. So you have a partial derivative of mu x. Yeah, let me touch this point a little bit later. First, let me distribute this as we have the partial derivative of this times this. So we need to use the product rule. Is this times the partial derivative of this times this times the plus this times the partial derivative of this. You know, it's like the product rule of a product that we are going to take the derivative, but with partial derivative. So here would be mu of xy times the partial derivative of mxy with respect to the y plus m of xy plus the partial derivative of mu xy divided by in dy equals the mu xy times the partial derivative of nxy divided by in the, or with respect to the x, plus, I'm running out of space, so I will just put times n times the partial derivative of mu with respect to the x. Let's associate the terms that has the mu. So it will be this term and this term. Let's put it here, and the other is the other side. So we have mu of x and y. I'm going to factorize everything. So mu of x and y times d mu x y dy here. This, and because I'm going to factorize it in the next step, xy times the partial derivative of n in the x equals to this first and partial derivative of mu in x minus m partial derivative of mu in y. Now we factorize everything and we have mu of x and y is equal to the partial derivative of, times the partial derivative of mu of m with respect to the y minus the partial derivative of n with respect to the x is equal to the partial derivative of mu with respect of, we cannot factorize this. So n partial derivative of mu with respect to x minus n partial derivative of mu with respect to the y. Alright, now we will do the assumption that the assumption is not only we're assuming that we have an integrating factor that will make this equation equals to 0, but also that the integrating factor only depends on x. So if only depends on x, here is mu of x. There is no mu of x and y. Here is just mu of x. For that I was trying to keep x and y, but I'm running out of space anyway. So this you leave it like this, the mu of x, but here when you take the partial derivative of mu with respect to y, this would be 0. And so actually I forgot to do a previous step, that was leave this alone. So you have partial m in the y minus partial n in the x is equal to 1 divided by mu times n partial mu in the x minus n partial mu in the y. Now if mu only depends on x, when you take the partial derivative of mu with respect to y, this is 0 because only depends on x is like a constant when you take the partial derivative with respect to y. So this will go away, and so you have the partial derivative of mu of m with respect to y minus partial derivative of n with respect to x is equal to 1 divided by mu times n times partial derivative of mu with respect to the x. Alright, now we know that when you have 1 divided by something, this is the derivative of natural log of that something. So you have natural log of mu. If you take this derivative with respect to mu, you have 1 over mu. So here you can put this as, instead of having here 1 times mu, you put the, not partial, you put the derivative of natural log of mu in mu. And so you can cancel this and you get partial derivative of m in dy minus partial derivative of y in dx is equal to, you cancel this and you have n times the natural log, or well, the derivative of the natural log of mu with respect to x. Here, if you know mu is only depending on x, now you will leave this alone and you will divide everything by n. So everything divided by n equals to this, the derivative of the natural logarithm of mu with respect to dx. And this is all divided by n. And next, if you integrate both sides here with respect to dx, you will have, well, this would be whatever, let me call this g of x, and so you have the integral of g of x is equal to the integral of the derivative of the natural log is the natural logarithm of mu. Next, mu is equal to, you know, natural logarithm is logarithm base e of mu, that is, which is the exponent at which we have to elevate e in order to get n, mu. So e to the integral of dx in dx is equal to mu, and mu is our integrating factor. So that is, the integrating factor would be e to the integral of the partial derivative of m with respect to y minus the partial derivative of m with respect to x, all divided by n. This is not always possible. I think that we're going to see examples of this. But that is if mu only depends on x, and you will see that when you do this. If you have only x, things like that, you can do it. If you have only y's, you will need to find a integrating factor that will depend only on y. That, we are going to see it in a minute, or it depends on the time if I do it in the next video. Or if you have x and y's here that you cannot cancel, so there is no integrating factor that would help to do this equation, or to make this equation exact. And I suppose that we are going to continue in the next video.